Welcome to this presentation on the cardiovascular system, specifically on blood. This is the second of three presentations covering the cardiovascular system. Today we'll only be looking at, in Chapter 18 of Blosson, we'll be looking at the overview of blood, 18.1, the production of formed elements, 18.2, and then we'll continue into 18.3 on erythrocytes and finish up with 18.4 on leukocytes and platelets. Note we will not be going on to hemostasis, fancy word for blood clotting, or on to blood typing. Let's get started on this fascinating journey into what blood is and all of the special things that blood can tell us. Number one thing to remember is that blood is a connective tissue. We know this. This is not new to us. We learned that blood is a connective tissue, a liquid connective tissue back in chapter 2 when we were studying histology. Recall that blood is a collection of loosely arranged cells surrounded by an extracellular matrix in which there are proteins. And while the proteins in blood are different than the proteins in connective tissues, the other connective tissues, like tendons or ligaments or in the dermis, it still meets the general characteristics of a connective tissue. When we discuss blood, we're going to be talking about what makes up blood. And the first thing to be aware of is that blood has a number of cellular elements. These are referred to as the formed elements. And these you've at least heard of. These are red blood cells. You might see RBCs. You might also see erythrocytes. That's a word that'll come up here in a moment. There are white blood cells or WBCs, also called leukocytes. And then finally, there are cellular fragments, commonly referred to as platelets. In addition, there is the extracellular matrix, which you know the liquidy portion of blood is referred to as plasma. Now, there is one other liquid connective tissue, and that is lymph, and we'll discuss that a little bit in an upcoming lecture on the lymphatic system. So let's start off with just understanding what formed elements are. In this diagram, we see red blood cells or erythrocytes are shown, and we see these cells with a indentation. If you flip the cell over, you would see the same indentation on the other side. This shape is referred to as biconcave. You saw red blood cells back in Lab A when we were discussing hypo and hypertonicity. And that is when you saw red blood cells used as an example of what happens to cells when they're in different sorts of environments. In addition to red blood cells, there are platelets. Now, this diagram is not to scale. Platelets are not as large as red blood cells, but here you see both inactivated platelets. This is how they appear in your blood most of the time, smooth, irregular fragments of cells. And when they become activated, when there's damage to a vessel wall, the platelets become activated. They get these extensions, and we'll learn more about how platelets are a vital part of blood clotting. We won't be going into the specific details, but you'll hear me talk about how platelets are involved in clotting your blood. And then finally, there are white blood cells, and white blood cells come in 5 basic flavors. And we'll be describing what each of these cells does individually later in this presentation. For now, just know that the white blood cells are all a vital part of your lymphatic system. They are all involved in fighting off infection or foreign antigens, things that the body takes in that might be damaging to the body. And we'll talk about monocytes, lymphocytes, eosinophils, basophils, and neutrophils as our discussion continues through. So what does blood do for us? Some of this may be obvious, some of this may be new to you. The primary function of blood is to deliver oxygen. That's probably the first thing that you consider when you hear about the functions of blood. But we don't want to forget that when blood is pumping around your body, you're also distributing nutrients, you're also picking up and removing waste products, and don't forget you're also distributing hormones and you're distributing water. So all of these things are important as we consider the transportation and what blood is doing for us. So as you eat, think digestive system, and as those food uh, molecules are absorbed into your intestines, those nutrients are going to be absorbed into the bloodstream, and they are first going to go to the liver. There, those nutrients will be processed and released back into the bloodstream. Now, you've heard a little bit about this in the digestive presentation, and you'll hear more about the blood vessels involved with this when we get to the next presentation on blood vessels. The oxygen you breathe is going to go and be distributed through your body. And the oxygen, of course, is picked up in your alveoli, in your air sacs of your lungs. And the heart is going to be pumping that blood around the body. Again, the endocrine glands are releasing hormones, and most hormones are distributed quite freely through the blood. Finally, we have carbon dioxide, which is a waste product of our metabolism. We also have waste products from our digestive processes as well that are transported to the kidneys for release. The liver is also helping to detoxify and get rid of molecules from our body. Defensively, our blood is incredibly important in fighting off disease. We'll see that some of the white blood cells are specifically designed to destroy bacteria that come into our body. We'll also see that other white blood cells are specifically looking for cancerous cells. Remember, we're making cancer cells every day, and our immune cells, some of those lymphocytes, are fighting off those cancerous cells and destroying them before they're able to take hold in our body. Other cells are infected with viruses, and we'll see how those some of those white blood cells are fighting off viruses as well. Also related to defense, as I mentioned, platelets are involved in clotting your blood. So if you cut a blood vessel, the platelets are activated. They set up a cascade of events whereby a blood clot is formed, again, defending you against significant blood loss. Also, blood is hugely important in regulating your body temperature. We discussed this way back in chapter 1 and chapter 2 a little bit. You know that when you are exercising, that your body is going to try to release heat, that blood vessels up in your dermis are going to dilate and release heat, whereas on a colder day, those same vessels are going to constrict, and that is going to help you conserve heat. Again, this is an important homeostatic process. We also have in our blood a number of buffers. Buffers are compounds that are going to help keep the blood pH the same, and we'll see that that's also a very important role of blood. So, if you have blood drawn, if you're giving blood for the Red Cross perhaps, or you're in a clinic and they're drawing some blood for testing, one thing that we can do with our blood is to perform a hematocrit. Now, hematocrit is a term we know from our vocab. Hemato means blood, and crit, recall, means to separate. Now, hematocrit refers to two things. One, it refers to when you draw blood, you can put it into a centrifuge. You can then separate the blood into its components, and when you do that, you'll see that you also get a hematocrit value. And a hematocrit value is the percentage of your total blood volume that is composed of red blood cells. So let's take a look at a picture here to better understand this. So here is a tube of blood. And in this example, what I want you to see is that you would take some blood. This could be a small volume, and you're going to spin it down in a centrifuge. And when you spin it down in a centrifuge, the blood is going to separate. The larger things will go toward the bottom of the tube. And in a normal blood sample, you will see that the red blood cells will pellet toward the bottom of the tube. There will be a very small fraction in the middle, referred to as the buffy coat, and that is where the white blood cells and the platelets will land in the centrifugation process. And then everything above that will be the liquidy plasma. And in the plasma, this is where we have the water, proteins, nutrients, electrolytes, hormones, waste products, everything that is being carried in your blood is dissolved in that plasma layer. The hematocrit value, therefore, would be the percentage of this. So we see that the tube, this represents a certain volume of blood. And you can see here that the hematocrit value, the percentage of red blood cells, is a little bit less than 50%. If you spun down your blood and you had fewer red blood cells or more red blood cells, that would be reflected over here. Let me introduce these numbers to you. In this unit, there is going to be, or there are definitely going to be, more numbers than any other unit that we have had in this course to date. In a normal male, normal hematocrit is between 42 and 52%. That is, when you take a man's blood and you spin it down, the red blood cell fraction should be between 42 and 52%. Roughly, I always remember plus or minus 50% a little bit. Now, I do want you to know these ranges. For a normal female, it's going to be lower. A female is going to have fewer red blood cells in blood, 37 to 47. Again, these are normal hematocrit values. If instead a person, we took their blood and we spun it down and there was far less or far fewer red blood cells, we would say that that person has anemia or is anemic. So, for example, if the hematocrit value was 30%, and that was a female's blood, we would say that she is anemic. If instead a man had a hematocrit of 40%, we would say that his blood was anemic, but notice that 40% for a female would be normal. Conversely, if you spin the blood down and there's a higher percentage of red blood cells than normal, the diagnosis is polycythemia. Recall from our vocab, emia is an abnormal condition of the blood where there are many cytos, cells. And red blood cells are by far the most prevalent type of cell. So polycythemia, too many red blood cells. This is not as common, but you can imagine that if there is too many red blood cells in a volume of blood, that blood is thicker and that blood has it's going to have more difficulty traveling through the body, through the blood vessels, and this can lead to some other issues as well. So polycythemia, too many, anemia, too few, normal hematocrit, mama bear, perfect value of your blood. So do know these numbers. So let's look at a few other characteristics of blood. Number one, you know that blood is red. Blood is naturally red. Blood has two sort of different colors of red, however. If you're looking at freshly oxygenated blood, blood that has just come from the lungs, it is going to be bright red. We'll understand why this is in a moment. But when that blood delivers oxygen to the tissues, that blood becomes more of a dusky red, or I always describe it as more of a darker burgundy or bricky brown sort of red. And that is because in your red blood cells, there is a pigment. Pigment is simply a molecule that has color. And the molecule that gives your red blood cells its color is a protein called hemoglobin. IN, it's a protein, hemo, blood, and this protein is globular in shape. You'll see that in a few minutes. And depending upon how much oxygen is bound to the hemoglobin, it will change the color of the blood. Number two, blood is viscous. We know blood is thicker than water. We hear that phrase, blood is thicker than water. It's about 4 to 5 times thicker than water. That viscosity, that thickness, is important for the way in which blood travels through your body. There are proteins dissolved in your plasma as well as those formed elements, and they contribute to the thickness of the blood. That thickness has a dramatic effect on blood pressure as well. Blood pressure is something that we'll be discussing a little bit in labs 8 and 9. Blood temperature. Your normal body temperature is about 37 degrees or 98.6 Fahrenheit. Blood has a temperature about 1 degree warmer, degrees Celsius, about 38 Celsius, or a little bit over 100 degrees Fahrenheit. This means that your blood is transporting that heat around your body. That's important for just normal body warmth and functioning. And it's also a reminder that if and when bacteria get into our blood, that our blood is a warm, nutrient-rich place where bacteria love to grow. So getting an infection, bacterial infection into the blood can lead to a septic situation. And diabetics, because they normally have a higher level of blood sugar, are even more prone to having bacterial infections. Another number to keep track of is that the pH of blood is about 7.4. That's a number I definitely want you to know. It ranges from 7.35 to 7.45, which means recall that neutral is 7, and anything above 7 is alkaline or basic. So a person's blood is not neutral. The pH of blood is a little bit basic or a little bit alkaline. And then finally, blood constitutes about 8% of your total body weight. Again, this is the person more of normal body size, average body size, but about 8% of the total body weight is made up of blood. Recall we've discussed that an average person has around 5 liters of blood. A larger person, males, will have between 5 and 6. More petite people will have between 4 and 5. So why do you think men have more red blood cells? Men have more red blood cells because on average, men have greater muscle mass. And muscle is a very vascular tissue. You know that muscle is red in color. It has a lot of blood volume, and that volume of blood is necessary to keep a larger muscle mass running in perfect way. Another thing is that testosterone levels in the male actually drive the number of red blood cells up to help match with that muscle mass. So there's a number of reasons why men have a naturally higher hematocrit value. So we know about the formed elements now, and we've talked a little bit about the functions of blood. Let's take a look at the plasma, the liquidy portion of blood. It's mostly water. It's about 92% water. Okay, 92% water. Everything else that's mixed in there, proteins, electrolytes, are suspended in that water. And the other big thing that is suspended in that plasma are proteins. About 7% of the plasma volume is proteins. Now, those proteins fall into 3 basic categories. Number 1, albumin. I want you to remember that albumin is the most abundant, AA. Albumin is the most abundant of the plasma proteins. You may have heard of albumin. Albumin is also the main protein that we find in egg whites, for example. Also of note is albumin is produced in the liver. So you are making albumin in your liver. And there's a number of features and important things that albumin does for you. But what I want you to focus on for this class is that it's albumin that has the most significant effect on the osmotic pressure of your blood. That is, the ability of your blood to hold water inside your blood vessels and also for your tissues to draw water across has to do with albumin. We'll talk more about this as we go through this unit. This also means that a person who has liver damage, liver disease, cirrhosis of the liver, if their liver is not healthy and not making adequate albumin, these individuals oftentimes exhibit large bellies. That large bellies is called ascites, and that ascites is the result of too much fluid in the abdominal cavity. So liver damage can lead to low albumin, which can lead to a buildup of fluid in the abdominal cavities, and that is referred to as ascites. The second most common protein are collectively called the globulins. Now, you may know these as another name. These globulins are also more commonly referred to as your antibodies. Okay, your antibodies or your immunoglobulins. In addition to being your antibodies, these proteins also are involved with transporting other important molecules around in your blood. But we're going to focus on the antibody portion for the globulins. Antibodies are proteins that are protective against foreign antigens. So if something comes into your body, and if you have an antibody against that particular protein or molecule, then your antibodies will sense that, and your immune system will very readily attack whatever it is that that antibody is designed to detect. Finally, there is fibrinogen. Fibrinogen is a protein that is also made by the liver. It is essential for blood clotting. And again, if a person has liver damage or a faulty liver, they're going to have issues with blood clotting as well. That's a really good connection if you're looking for a connection with the cardiovascular system, with the digestive system, because we think of the liver as being primarily a digestive organ. So here's a table. Let's take a look at this table. We have in blood, your blood is about 37 to 54% formed elements. Now, again, that's the entire range. We know that in those formed elements, 99%, by far, the vast majority of your formed elements are red blood cells. Then leukocytes, white blood cells, and platelets make up less than 1% of your formed elements. This range is so significant because remember, women have a lower hematocrit and guys have a higher hematocrit. So that's why there's such a range here. In addition to the formed elements, there is plasma. Again, the range is just the inverse of the formed elements. And in the plasma, we have about 7% proteins. What I just described to you, albumins being the most common, globulins or immunoglobulins are second largest group, and then the fibrinogen. In addition to the proteins, there are a whole host of hormones and enzymes, what are collectively referred to as your regulatory proteins, but notice that's a very small percentage. The enzymes and the hormones in your blood are very low in concentration, extremely important, very, very critical molecules, but their numbers are very low and their concentrations are very low. And then you also have the nutrients, waste products, and gases like oxygen and CO2 also dissolved in your plasma. Some of the other features over here we'll touch on at times. If I don't discuss it at some point, it won't be important for you, but this does mention that albumins are made by the liver, as is fibrinogen, and that it also tells us where these formed elements are made, and that is a red bone marrow, and we'll be discussing that here in just a second. That's an important table to review. Don't forget to be entertaining these questions. These questions are really going to help you appreciate all of the facts that are being discussed. So that brings us to the end of 18.1. Again, all we've discussed is what are the main components of blood. Blood is a connective tissue. It is composed of formed elements, proteins, and other gases, nutrients, hormones dissolved in there. So just know the basic breakdown. Also, review those hematocrit values and appreciate the meaning of anemia and polycythemia. Getting into 18.2, now let's take a closer look at those formed elements. The production of formed elements is referred to as hematopoiesis, the same word hemopoiesis. They're both correct. Hemo and hemato both mean blood. Poiesis is the production of the formation of something. It takes your body about 4 to 6 weeks to replace blood cells. This is why if you go and you give blood at the blood clinic, they will only allow you to donate blood every 6 to 8 weeks, because we need to give your body plenty of time to replace all of those blood cells, the red cells, the white cells, and the platelets that have been removed from that donation. When you give blood, you're usually giving about a pint, about 500 mils or so, and the body can very quickly replace the plasma. Remember, plasma is 92% water and about 7% proteins. And your body can quickly replace the water and quickly replace the proteins. This is why you can go and give plasma 2 to 3 times a week. So you can give plasma at the plasma center multiple times a week, but you can only donate whole blood occasionally every 6 to 8 weeks. So, where is blood being produced in your body? In the early embryo, there is hematopoiesis occurring in a number of places, including the fetal liver, the fetal spleen. But in you and me, our hematopoiesis is occurring only in the bone marrow, and not even all bone marrow, but only in some. So in adults, hematopoiesis is largely restricted to your cranial bones, your flat bones of your cranium, think frontal bone, your pelvic bones, think the os coxa, your vertebra, right, your irregular vertebra, your sternum, and the proximal epiphyses of both your humerus and your femurs. So that is the only place where you are actively making blood as an adult. All blood, all formed elements are made in your red bone marrow. Now, there is the possibility of your body making these formed elements in your liver and spleen, but that is only in an extreme situation where your bone marrow is not working. Typically, your liver and spleen are not making blood. Only in a situation where your bone marrow is destroyed would hematopoiesis be initiated by these extramedullary sites. So you understand that word extramedullary, outside of the regular medullary cavity of your bone. So all of your formed elements are coming from the red bone marrow, typically, and there is a hierarchy of differentiation that we've talked about a long time ago. You know that in the early embryo, the zygote, that all of the cells in the body are totipotent, and that they can give rise to any cell type in your body. And then recall that those totipotent cells go through differentiation, they become more specialized, and totipotent cells become pluripotent. Then they move on and become multipotent, and eventually down to omnipotent, and finally unipotent. In your bone marrow, there is a stem cell referred to as a hematopoietic stem cell. It's also referred to as a hemocytoblast. And these are essentially oligopotent stem cells. They are only able to differentiate into a very limited number of cell types. And from these hemocytoblasts, all of your formed elements are going to be created. Now, there's a whole series of chemical and hormonal steps that are necessary for this to happen, and we're not dealing with those steps. But I do want you to appreciate the following that initial hemocytoblast can become one of two types of cells. It can go on to become a lymphoid stem cell. Your lymphoid stem cells are then going to be able to make all of the lymphocytes. So the name tells you, lymphoid stem cells become lymphocytes. These are your T cells, B cells, natural killer cells. We'll discuss these a little bit later. That process of making those cells alone is referred to as lymphopoiesis, right? The process of making the lymphatic cells. The other type of cell that the hemocytoblast can become is called the myeloid stem cell. And the myeloid stem cell can become many different types of cells, including all of your red blood cells, your megakaryocytes, and most of the other white blood cells. So let's take a look at this diagram to make sense of this. So in your bone marrow, you have a hemocytoblast. This cell can undergo differentiation to become either a myeloid stem cell or a lymphoid stem cell. If this cell is a lymphoid stem cell, it will go through further steps of specialization and differentiation and become flavors of lymphocytes, B cells, T cells, natural killer cells. We'll only discuss these briefly in this unit this year. So very limited, right? L for limited, only lymphocytes. In the myeloid side, we're going to become a multitude of other cells or many different cells. So again, through different chemical signals, which we're not learning about, we're not even going to worry about these precursor cells. But what we see is that the myeloid stem cell can become megakaryocytes. Megakaryocytes are where platelets come from. Also, these myeloid stem cells can become erythrocytes, red blood cells, basophils, neutrophils, eosinophils, and even the monocytes. So these are all of the multitude of other types of formed elements. So don't make this too difficult. Just know that there is one cell, the hemocytoblast, that can become either a myeloid, many cells, or lymphoid, more limited. And all of your formed elements, all the different flavors of formed elements, are formed from that one hematopoietic stem cell. This is a nice animation that goes through this, but don't get too caught up on the intermediate details. Now, how that happens and how these different formed elements are initiated and controlled, there is one hormone that I want you to understand more specifically, and that is erythropoietin, EPO. You can break this down. It ends in IN. It's a protein, and it is somehow erythro, right? Red blood cells, POE production of. So this is the protein that is going to initiate the production of red blood cells. Remember, erythro means red. It is made by the kidneys. So keep track of where these different molecules are made. And the kidneys, not only are they filtering your blood to get rid of waste products, but your kidneys are also filtering your blood and they are monitoring the oxygen levels of your blood. And when your kidneys filter your blood and sense that there is low oxygen levels, your kidneys will then upregulate the production of EPO, and that EPO will then travel through the blood from the kidneys, go to the bone marrow, and prompt your bone marrow to increase the production of erythrocytes. Now, EPO is used clinically to help fight anemia. EPO is given to patients sometimes following a bone marrow transplant or following a chemotherapy regimen to increase their number of red blood cells. But we also hear about EPO being taken as a banned substance by some athletes who want to increase their red blood cells. Well, that would be advantageous if you were a long distance runner or a cyclist and you needed your body to maintain higher levels of oxygen in your blood to support the increased demands of the athletic event. So there are individuals who take synthetic forms of EPO. Again, this is a banned substance, but this is going to cause their hematocrit to go up, right? Your red blood cells go up, your hematocrit values go up. You might even become polycythemic, which could be a problem with blood clotting. But you also would have an increase in red blood cells and oxygen carrying capacity of your blood. So I do want you to know about erythropoietin. We will discuss erythropoietin again when we get to the urinary system and the kidneys. Additionally, and this animation will walk you through that, additionally, there is thrombopoietin. And again, now that we appreciate what these words are, we can understand this is the protein that increases the production of platelets. This is also made by the liver, and this protein would trigger the development of more megakaryocytes, which would then form more platelets. Cytokines are also an important group of molecules for the development of these cells, and we can appreciate this word, kind, think kinetic, movement. And so these are molecules that cause cells to migrate, to move, to be recruited to different parts of the body. And we're not going to discuss the colony stimulating factors, but these are a group of molecules in the body that also help regulate your formed elements, as well as the interleukins, another group of cytokine type molecules that are important in hemopoiesis. Again, there is a vast number of proteins that are involved in the production and maintenance of your blood cells. This little inset gives you a little story about blood doping and how EPO has been used to increase the production of red blood cells, and again, is now a banned substance. Most famously, Lance Armstrong, winner of 7 Tour de France's bike races, had been stripped of his titles after it was discovered many years ago that he had been illegally doping with EPO-like molecules. Also of significance that you can appreciate are bone marrow biopsies. This is where a sample of red bone marrow is taken from the pelvis, usually, to test for blood cancers and blood disorders. Or you may have heard of bone marrow transplants, and this is where the bone marrow from a healthy patient is donated to a person whose bone marrow is failing. So if a person has a bone marrow cancer, what they'll do is they will completely wipe out that person's own hematopoietic processes in their bone marrow. They'll irradiate that person and bring them basically to a totally immunocompromised state. They will then insert from a healthy person bone marrow that has been carefully selected to not be rejected. That bone marrow will hopefully graft into that person and then take over the production of blood cells for that individual. This animation goes through the biopsy of the bone marrow, and typically that sample is taken from the iliac crest, very easy to get to, very close to the surface of the body, basically bore through the ilium, bore through the bone, and then collect a large sample of bone marrow and send that off to the clinic for genetic testing and for all sorts of other testing of the blood. Of interest here is that if you have a bone marrow transplant, so you've had some sort of cancer, you have received bone marrow from another patient, if you were to now commit a crime after having received a bone marrow transplant, your blood cells would not be your own genetics, right? You are now producing formed elements, red cells, white cells, and platelets that are genetically identical to the donor and not your own. And in your in your blood, you would no longer be as easily traced as the perpetrator of that crime. There's always a few interesting stories in crime mysteries whereby a bone marrow transplant patient is the bad guy, and it creates all sorts of issues with identification. So that brings us to the end of the production of formed elements. Just appreciate this is happening only in your red bone marrow. In you and me as adults, only happening in a limited number of places in your body, and that there are factors that are going to differentiate that hemocytoblast into different cells and eventually form all of the different formed elements in the blood. These questions will guide you through this. Now, moving on to 18.3, this chapter is all about erythrocytes. So we're going to be looking at the anatomy of red blood cells, looking at the life cycle of red blood cells, as well as looking more carefully at that protein hemoglobin. So again, erythrocytes, aka RBCs or red blood cells, they are by far the most common of your formed elements, making up over 99% of all the formed elements. And in just a tiny, tiny little drop of blood, there are millions and millions of red blood cells. Let's take a look at those numbers. So here's a table you're going to refer back to a couple of times. Again, if I mention the numbers individually, that's a number that you need to keep track of. If you like numbers, great. If you don't like numbers, I'm sorry. You'll have to keep track of these. Maybe a few note cards would be advisable to keep track of these numbers. So what we're talking about in this section will be the red blood cells in a microliter of blood. This is a tiny, tiny little drop of blood. This is 1/1,000,000th of a liter. That mu is microliter. And in a microliter of blood, there's going to be around 5 million red blood cells. Now notice the range from about 4.4 to 6 million red blood cells per microscopic drop of blood. Remember, men will have more and women have fewer, and that's why there's quite a range here. The shape of red blood cells will be that biconcave shape. I haven't mentioned it yet, but red blood cells do not have a nucleus. We'll figure that out here in a second. And they are naturally red in color. The purpose of red blood cells is to transport oxygen and CO2 through your body. And red blood cells hang out in your body for about 4 months, for about 120 days. So these numbers are important. 120 days, 5 million on average. And we'll also be looking at the size of red blood cells in a moment. The other cells, the other formed elements are mentioned in this table. White blood cells at the bottom, platelets. I'll come back to these numbers as we move through the rest of this chapter, but you'll want to go back and look at this table. And again, only focus on those things which I have described specifically in this presentation. So here we go. In every microliter of blood, 5.4, right, on average for men, and on average 4.8 million for women. Again, just a range. I always remember just about 5 million. That number will be sufficient for what we're talking about. Erythrocytes account for approximately 25% of all of the cells in your body. 25%. Huge. A red blood cell has a mean diameter, an average diameter of only 7 to 8 micrometers. Many books will say 7.5, right in the middle. 7.5 micrometers. And again, their job is to carry oxygen from your lungs through your body and also pick up waste product CO2 and deliver it also back to the lungs for exhalation. Erythrocytes are, again, like all formed elements, formed in the red bone marrow. They largely mature also in the red bone marrow, and they're going to leave the red bone marrow and go into the general circulation. As they are leaving, they're going to lose their nucleus and most of their organelles. Okay, so red blood cells are barely even cells. Remember, we talked about cells way back in chapter 1. What are the characteristics of cells? And one of the characteristics of a cell is that they can reproduce, that they have DNA, that they can undergo a cell cycle, that they can produce more of themselves. Well, in fact, red blood cells, mature red blood cells, cannot do that. They don't have a nucleus, they don't carry DNA, and they don't have most of the organelles either. So, red blood cells, once they are traveling in your blood, are essentially nothing more than oxygen and CO2 carriers. This is what they do. Uh, there is a cell called a reticulocyte. This is the cell that is sort of your last stage before it's a mature red blood cell. They represent a very small percentage of your total red blood cells, and they have a little bit of the remnant organelles, but by far the vast majority of your red blood cells are anucleated with very few, very few organelles. In fact, that reticulum word just refers to all the ribosomes that are initially present in red blood cells but are quickly lost. Again, erythrocytes are biconcave discs. Recall when we were in Lab A, we talked about how cells can change their shape. Cells put into a hypotonic environment, think pure water, will swell and can even burst or lyse. And recall that cells that are put into a salty or a highly tonic solution will crenate or shrink. It was red blood cells that we looked at as an example of tonicity back in Lab A. So you've seen that these cells can change their shape. They can kind of squiggle their way through and are very flexible as a result. Recall that, here they are, these cells are biconcave. They have about 7.5 microns. 7 to 8 micrometers across in their size. And this is important because, and we'll talk more about this next time, but go back up. This is important because your capillaries, your most delicate little blood vessels, only have a 8 to 10 micron diameter. So red blood cells have to squeeze, rather, they'd be really flexible and squeeze and go through those smallest vessels. We'll see examples of this as we get to the blood vessel chapter next time. Inside your red blood cells, recall, they are lacking a nucleus, they're lacking their organelles, but they largely are a big collection place for a protein called hemoglobin. Hemoglobin, hemo, again, blood, a protein, IN. These are globular or circular, sort of spherical shaped proteins. It is a protein, and also associated to it is an iron. In every hemoglobin protein, there are 4 subsets. They're called each a globin. We're not going to worry about differentiating between the alphas and the beta, but you'll see that there's 4 of these. And in the center of each of these 4 globin subunits, there is a red pigment molecule called heme. Again, it's the heme group that gives blood its red color. And to each of those heme groups, there's an iron ion bound. Fe is the symbol for iron. This animation will help you understand that as we look at this diagram. All we're going to see here is that there are 4 of these units, right? They're labeled betas and alphas. We don't care about that. In the very center of each of these 4 units, there is a circular unit. That is, the red unit is the heme group. And to each heme group, we have an Fe and iron ion bound. So every hemoglobin molecule has 4 irons, and to each of those irons, an oxygen molecule combined. So that means that every hemoglobin can only hold a maximum of 4 oxygens. Okay, each iron group holds 1 iron molecule, and so therefore each hemoglobin can only transport a maximum of 4 oxygen molecules. Well, here's what's mind-boggling, is that every one of your red blood cells has about 300 million hemoglobin molecules. So if we take 300 million times 4, that means that every red blood cell can carry over 1 billion oxygen molecules. Now, when your red blood cells go to the lung, and let's think about our heart here for a second. The right ventricle is going to pump, send blood out the pulmonary trunk, pulmonary arteries, off to the lungs. There, the hemoglobin is going to be recharged or pick up a fresh supply of oxygen. So when hemoglobin is leaving the lungs and coming back through the pulmonary veins, going to the left atrium, that blood, those hemoglobin molecules have picked up oxygen. They are completely saturated with oxygen, and we call that form of hemoglobin oxyhemoglobin. Makes sense? It is full of oxygen. It is bright red. Now, as that blood transports through our body, it's going to drop off some of that oxygen. And now that hemoglobin will not be quite as bright red. It's going to be more of a darker red. And that form of hemoglobin, where it doesn't have full oxygenation, is called deoxyhemoglobin, right? The deoxygenation, if you will, of hemoglobin. Now, we never completely lose all the oxygen, but let's say only 3 of the 4 globins is now oxygenated. So that is going to cause the hemoglobin to be a darker red color. Sometimes, well, in all situations, but hemoglobin also carries some of your CO2. And the CO2, when it's bound to the hemoglobin, is called carbaminohemoglobin, right? We just see the carb in the front, that's like the carbon dioxide unit. So when there's carbon dioxide attached to hemoglobin, carbinohemoglobin. Now, your ability to get tissues oxygenated and for your normal metabolism work, we need to have a constant supply of oxygen. That means we have to have a constant supply of iron also available to the making of our hemoglobin and carrying oxygen to our tissues. Anemia, therefore, can be a lack of red blood cells. It can also be caused by a lack of iron. So if you have insufficient iron in your body, then you cannot keep your hemoglobin molecules formed properly, and low iron can lead to anemia as well. If you are insufficient in hemoglobin, your tissues are not receiving enough oxygen to be working at their maximum. And if you have low oxygenation going to your tissues, you are said to have hypoxemia, right? Or you're hypoxic. When you go to the doctor and they put that pulse ox on your finger, and they're measuring your oxygenation levels. Basically, what they're measuring in that little unit is how red is your blood. So that unit is able to detect how red your blood is. And if it's bright red, then you have a high oxygenation. If it is a lower number, then the unit is detecting a lower coloring of your hemoglobin and you are hypoxic. Remember, as I said, your kidneys, as they're filtering your blood, are also looking to see if you are hypoxic. And if your kidneys say, hey, you don't have enough oxygen in your blood, that is when the kidneys will release that EPO, and that will cause your erythrocyte production to be increased. Now, we can get a higher hemoglobin level from EPO naturally produced by our kidneys, but we can also increase our red blood cells by going to higher altitudes. So you may be aware that when individuals go, for example, to the Himalayas and they're climbing K2 or we're going Mount Everest, that mountain climbers can only go so far. They climb a little bit each day. And they do that for a few reasons. One, it's extremely exhausting, right? They're physically exhausted. But number two, as you climb higher up a mountain, you are going to higher and higher altitudes where there's less and less atmospheric pressure. That means that the body's not getting the same amounts of oxygen. And you have to wait for your body to adjust to that increased altitude or that decreased oxygen availability. If you climb up too quickly, you'll get altitude sickness. And so we wait and we wait and we wait because it takes about 5 days for your body to adjust to those altitude levels. Another way of thinking about this, if you were to fly right now to Denver, the mile high city, and you were to try to do your normal exercise routine in Denver, you'd be winded. And it's going to take a few days for your body to increase its erythrocyte levels. Your kidneys will detect that you're at a higher altitude. Because of that lower atmospheric pressure, your body will not get as much oxygen in, and your body will respond by increasing its EPO levels. About 5 days later, you will have adjusted. So again, mountain climbers need to adjust. If you're traveling, you would need to wait for your body to adjust. And this is also why, for example, when football teams go out to Denver to play the Denver Broncos or the University of Colorado, they'll try to get out there a little bit earlier than normal because they want the athletes have their body adjust for a few days before the game naturally. And this is also why you'll see oxygen tanks on the sidelines in those high altitude games. If you wanted to have a natural advantage, if you're running a race in Muskegon, you're running a marathon, and you had the resources, you could fly to Denver or fly to the Himalayas or fly to some high altitude place, let your body adjust for a week or so, fly back to Muskegon, run that race, and you will have now naturally increased your hematocrit by naturally increasing your EPO levels, your hematocrit, and therefore your ability of your body to deliver oxygen in that athletic event. And you will therefore also have an advantage in that competition. And you haven't broken any rules by doing so. Let's talk about the life cycle of erythrocytes. You are making, this is amazing, you're making about 2 million more red blood cells every second. 2 million, 2 million, 2 million, 2 million. It also means, recall, that you are also losing 2 million red blood cells every second through apoptotic events. So keep that in mind. 25% of all of your body's cells are red blood cells, and they are being made in the bucket levels, right? 2 million per second. Let's look at a couple of facts about that life cycle of red blood cells. Number one, as we discussed, we need iron. If we don't have enough iron, we can't make enough hemoglobin. If we don't have enough hemoglobin, right, we basically have a resource problem. So we must have iron. In addition to iron, and we get iron from our leafy greens, we get iron from meats, from liver. So it's important to get those things. And we also need copper, We won't talk about why, but there's copper is necessary to make normal red blood cells. Copper deficiency can lead to a red blood cell deficiency. There's also zinc that is necessary. If you look at your vitamins, right, you're taking some vitamins, you've got zinc, copper, and iron, and B vitamins, specifically B12. B12 is the big one. B12 deficiencies can also lead to anemia. We have to have all of those things. Another fact to keep track of: erythrocytes, as I said earlier, live, hang out, circulate for about 120 days, about 4 months. And when they are worn out, you have macrophages hanging out in your liver and spleen, and even a few in the bone marrow that are looking for worn out red blood cells. And these macrophages will then destroy those red blood cells and then begin a process of recycling those components. So, what happens when these cells are broken down? Number one, the globin. That's the protein part of the hemoglobin. That's going to be broken down into amino acids. Those amino acids are then cycled through the body and are used to make other proteins. Number two, the iron group in your red blood cells is going to be sent back to your liver or your spleen. Your liver is a great place for storing iron. This is why eating the liver of a cow is a high iron source, because the liver naturally stores iron. And that iron will then be made available once again, traveling through your body back to your bone marrow for making new red blood cells. And then finally, that heme group, remember that little molecule that attaches to the iron, or the iron attaches to it. That molecule is broken down through a series of molecules, and I bet you've heard of one of these. It first goes to biliverdin, and you might know Verdi is, in other languages, a term for green. And then biliverdin breaks down to a molecule you probably heard of, bilirubin. Bilirubin is a yellow pigmented molecule. Where have you seen this before? Well, if a person has liver damage, then their body cannot break down heme normally, and that yellow hemoglobin, that yellow bilirubin, will collect in their eyes, and people with liver damage will have yellowing of the eyes, yellowing of their skin, because their liver can no longer break down the bilirubin. Where else have you seen this? The reason that your urine is yellow is because this bilirubin is excreted in part from the kidneys. Your feces are brown in part because of the breakdown of some of these bilirubin products. Okay, so our urine is yellow, our feces are brown because of the breakdown of this. Let's take a look at the whole story of the life cycle of red blood cells. So hematopoiesis is occurring in your bone marrow. The process of making red blood cells is erythropoiesis. And we've talked about the hormone erythropoietin as a driver of this process. Your hematopoiesis of all formed elements, but in this case, red blood cells, is happening in, for example, your hip bone and the proximal heads of your humeruses and your femurs. And from this, we're going to be making those prerequisite cells. Reticulocytes are released into the body, into the bloodstream, and we get those mature red blood cells. Those red blood cells are going to circulate in your circulation for about 120 days. After 120 days, as your blood is being filtered through the kidney or through the spleen, macrophages are going to detect the old, worn out red blood cells, and they are going to be broken down. When that red blood cell is broken down, what's going to happen? Well, the protein portion, the globins, are simply going to be broken down into amino acids and reused for other protein synthetic processes. Lysosomes are going to help with this process. Remember, lysosomes are organelles within cells. In this case, there's many of those lysosomes in macrophages as they break down these red blood cells. The heme group It's going to be separated into its two parts. The heme group is going to go to be that biliverdin, the bilirubin, the green and the yellow products. The liver then breaks that down further. And the iron group is also going to be transferred to the liver, but then used again, going back to making more red blood cells. Oh, I forgot to mention the other time that you have seen all of this is when you bruise, right? When you get punched or you hurt yourself and you have a bruise, you see those lovely colors of green and yellows and purples that happen with a shiner or with a bruise. Again, that is the natural breakdown of the heme groups in that blood that has leaked out of those broken capillaries that were damaged in the bruise. So we've seen this coloring effect of the breakdown of hemoglobin as we think about bruises as well. So be mindful of that 120-day cycle and how your red blood cells are distributed and recycling that. So again, anemia is a significant relatively common disorder. Now there's hundreds of different types of anemia. Many Americans and many people around the world deal with different kinds of anemia. The other time where you've heard about red blood cells and hemoglobin, way back when we were in the genetics section, we were talking about sickle cell anemia. Remember, this is a disease whereby hemoglobin is defective and has a mutation. And here's a normal red blood cell, but a cell with sickle cell anemia, at times the hemoglobin molecules, because of their mutation, will link end to end. That will cause the cell to change its shape into a long sickled shape. Now, the problem with this, a normal red blood cell is about 7 to 8 microns in diameter, and that's already a pretty tight squeeze for red blood cells to get through capillaries. But when these cells become sickled in shape, this cell is going to get into a capillary, clog up the flow of blood, and lead to all of the side effects, or many of the side effects related to sickle cell anemia. You can imagine in this animation, I'll talk you through that, but these abnormally shaped red blood cells are going to clog up the blood flow through that vessel. So again, we can have anemia for a whole number of reasons. There can be vitamin deficiencies, specifically B12. There can be copper issues. There can be iron issues. And then finally, there's another whole class of diseases called thalassemia. This is another inherited type of condition, more from people from the Middle East and the Mediterranean. It is different than sickle cell anemia, but it does also result in a form of anemia as well. I won't be asking you any specifics about thalassemia. So that brings us to the end of this section on erythrocytes. Remember also, too many red blood cells results in polycythemia. This would be an elevated hematocrit, and the problem with this is that you are making your blood thicker. This can raise your blood pressure, make it more difficult for your heart to pump blood. For a few moments, that's okay. If you live in higher altitudes, you're going to have a slightly higher hematocrit. But if it's a significantly high level, that can be a bigger problem overall for overall cardiovascular health. So continuing down, entertain these questions on erythrocytes, and we're going to go into our last section, and that is going to be on learning about leukocytes and platelets in 18.4. Okay, so the thing to remember about leukocytes is that they are the only true cell within blood. Recall, red blood cells don't have a nucleus and cannot divide and replace themselves. And platelets are not cells at all, but just fragments. And so at a crime scene, the only cells that are actually providing DNA evidence are the leukocytes. Now, these cells are very different than red blood cells. They are larger in size, as we'll see, and they do not carry gases, but instead are a major part of your body's immune system. They protect against invading microorganisms as well as cancerous cells, and they also help clean up debris. Again, platelets or the thrombocytes are essential for the repair of blood vessels and are activated. They release growth factors that are important for healing and repair. So let's start off with leukocytes. Now, these leukocytes, some of them are in the blood, some of them are transporting around the body and will go to the site of an infection. The number of these cells is important to also be mindful of. Within a microliter, there are only 5,000 to 10,000 5,000 to 10,000 white blood cells per microliter. Again, they're larger than erythrocytes, and they are the only formed elements with both a nucleus and a full collection of organelles. One of the most distinctive properties of white blood cells is their movement. Red blood cells spend their entire time circulating in blood vessels. Leukocytes, some of them routinely leave the bloodstream to perform their functions. And so while the white blood cells are traveling initially through the blood vessels, when they are called to the site of an infection, they will go there and they will then leave the blood vessels. We'll learn more about the structure of blood vessels in the next presentation, but from the capillaries, they're able to leave and go to the site of the infection. So this is known as emigration, or I see more oftentimes is termed diapedesis, in which case they will leave out of the capillary, and this video will help you understand that, to the site of the infection. Once they leave the capillaries, they're then going to be in the tissues, and they can set up directly attacking the organism or the cell that they are being called to destroy. Now, other leukocytes are going to instead simply take up residence in some of the lymphatic tissues. We'll be talking about the lymphatic system in a future lecture. Tissues like the bone marrow, the spleen, the thymus, or lymph nodes. To get an idea of this idea of chemotaxis, that is a chemical signal that brings the cells in. Here we see the skin. We see there's been a cut in the skin. These green, these represent the bacteria that have been introduced from this cut. If a few cells get up just in the epidermis, you can appreciate, remember there are some of those Langerhans cells floating in there, and those can take care of infection. But if it gets down below the basement membrane that you're seeing here, down in the dermis, now we're more directly toward the bloodstream. So the invading organisms actually send out signals. Those signals are now going to recruit cells from the bloodstream. And as we see here now, these white blood cells will leave, they'll squeeze out between those endothelial cells, and they will go to the site of the infection. And some of these cells are going to release chemicals that are going to directly invade or destroy these cells. So if this was a neutrophil, then it's going to release antibacterial factors. If it were instead a eosinophil, if this was a parasitic infection, eosinophils would instead come to the site of infection and would release anti-parasitic factors. Macrophages that are also here are going to then be able to engulf the bacteria and or clean up the mess as these cells are destroyed. You may wonder why white blood cells are called white blood cells. It has to do with the fact that when white blood cells come to the site of infection and they die in the process of defending the body, all of those white blood cells become what you know as pus. And pus is, in fact, a white fluid. And so when you see pus, what you're looking at are millions of white blood cells that have come to the rescue to fight off an infection. Let's talk about the different types of white blood cells. First of all, leukocytes come in two different classes or two different groups. First, there are the granulocytes, the granular leukocytes. These are going to have very abundant and visible granules. And we'll see over here that eosinophils, basophils, and neutrophils have, you can see just in the diagram, that there are these very significant granules. Those granules are going to be filled with antibacterial or anti parasitic factors that will be released upon activation. And then there are the agranulocytes, and as the name suggests, these have fewer or at least not obvious uh, of these granules. The agranulocytes include the monocytes and the lymphocytes. Let's go through what each of these is doing. You might wonder how these cells got their name. You recognize the ending of these eosinophils, basophils, and neutrophils. Phil, as in hydrophilic, right? An affinity for or a love of something. So it turns out eosinophils have an affinity for a dye called eosin. White blood cells, in and of themselves, are colorless. They are not like red blood cells that contain the heme group or the hemoglobin protein that makes them naturally red. So the only way to see white blood cells in the microscope is to dye the cells. And so years ago, they were playing around with different colored dyes, and they realized that you could differentiate the 5 different types of white blood cells in part by the color of the granules. And it turns out that in this cell, the eosinophil, the granules have an affinity for, a love of, the eosin dye. And it creates a reddish orange, sort of a salmon colored granule. So when you see orangey, reddish granules, those are eosinophils. Basophils, on the other hand, picked up a bluish, sometimes almost a black coloring. And so the other dye that is used is very basic. And so basophils, just by chance, have an affinity for this blackish blue dye. And so they are named basophils. Neutrophils, these granules don't have much of an affinity for either of these dyes. They stay more neutral in color and hence their name. So interestingly, these cells are simply named by the dye that is predominantly staining these granules. Monocytes and lymphocytes, again, don't have these obvious granules and are identified by different means. Let's take a look. And there are a number of different features for these cells. I'm going to give you one or two, and that's what you'll be responsible for knowing. So we see here the micrographs, the actual histological images. Notice that the red blood cells are in the background. All of these white blood cells are larger in size than red blood cells. And when we look at this, we can see the eosinophil has this reddish, orangey, in this case, more of a reddish color, the granules. And the basophils have the bluish black coloring, and the neutrophils, while you can still see the granules, are not predominantly red or black, and so they are more neutral in color. Monocytes, if you'll note, these red blood cells are slightly different scales. So this monocyte is huge. It's the largest of the white blood cells. Its size is the most prominent feature. I always remember that it's monstrous in size. So the monocytes are monstrous in size. Then the lymphocytes, their real telltale identifier is that their nucleus is very large and takes up the vast majority of the cytoplasm. Now, I will not be asking you to identify these different white blood cells from an image, but I think it's just curious to just make a note of how these cells are different in their appearance, and this is something that you will be asked to do in physiology. So let's go through these granulocytes. The first one on our list are going to be the neutrophils. So, what is it about neutrophils that I want you to know? Number one, I want you to know that they are the most numerous. So, the neutrophils are the most numerous of the white blood cells. Their claim to fame is that they are all about fighting bacteria. So, when a neutrophil is called to the site of a bacterial infection, it will release a number of enzymes and molecules, also a bleach like substance, all designed to kill off bacteria. So, if you have a bacterial infection, the neutrophils are going to be called to the site of the infection by that diapedesis process, and their granules are filled with antibacterial products. So neutrophils are all about killing off bacteria. Eosinophils are nowhere near as common. They only represent about 2 to 4% of all of your white blood cells. And their claim to fame is that they, again, stain with this acidic stain called eosin, which makes them reddish or orangey in color. And what these granules are filled with is the ability to fight off parasitic worms. So they are primarily going to be increased and go to the site of a parasitic infection. These cells also release antihistamines as well. And then lastly, you have the basophils, and they are the least common. So I always remember that the basophils are in the basement as far as their number, less than 1% of all the white blood cells, and they are the cells with the bluish black granules. Again, they are stained by an alkaline basic dye. They also are going to intensify any sort of inflammatory response. And they famously release histamines. If you were to have some sort of response to, let's say, freshly cut grass and you start to sneeze, your body perhaps is allergic to pollen. Your body is going to begin to get watery eyes. You're going to start to sneeze, and your body is desperately trying to get rid of that allergen. So you're sneezing, your eyes are watering, all for the purposes of getting rid of that very molecule that is driving your immune system crazy. But what will you do? Oftentimes you'll run to Walmart and you will pick up some antihistamines. And those antihistamines are going to stop that weepy eye and runny nose scenario. But basically, what you're doing is you're keeping the very thing in your body. You're minimizing the symptoms. Your body is trying to get rid of it, but you are going to now hold that substance into your body. So it's a little bit counterintuitive. Sometimes it might just be better to sneeze and get rid of it. But of course, we can't be running around being unprofessional sometimes. So we need to take some antihistamines. Now, the agranular leukocytes, again, smaller, less visible granules, not really obvious. The lymphocytes are the first group. They are, again, the cells that are made from the lymphoid stem cells. And these cells, there's a few different types of lymphocytes. I'm not going to go into that too much at all. But these cells are critical to fighting off cancer cells as well as cells that are infected with viruses. So they come in a few different flavors. There are natural killer cells, B cells, and T cells. What I do want you to know, again, is that these cells are, these lymphocytes are fighting off cancer cells and cells infected with viruses. The B lymphocytes, the B cells, are the cells that produce antibodies. We talked about those, the globulins being the second largest group of proteins. So the B cells are producing those antibodies. and the T cells are the ones more against the virus infected cells. The T cells are against diseased cells and viral infected cells. These animations will help you understand that as well. And then lastly, there are the monocytes. They are representing about 2 to 8% of all of the leukocytes. And they are the largest, up to 20 micrometers in diameter. The monocytes are the cells that will eventually differentiate into the macrophages. And we've seen a number of macrophages this semester. We have seen, for example, osteoclasts in bone. We've seen Langerhans cells in the skin. We have seen microglia in the brain. And we'll see a few other specifically named macrophages as we move through the unit. Just know that these macrophages all were once monocytes of some type and were all formed in the bone marrow. Now, leukocytes do not have a standard lifespan. There are so many different types and so many different reasons that these cells are produced that there is no standard number. So red blood cells hang around for 120 days. Leukocytes can be relatively short. I mean, just hours or days. So if you have a bacterial infection, your body's going to ramp up the number of neutrophils. Those neutrophils are going to go right to battle and probably die within hours. Other of your lymphocytes, the ones that make antibodies, are going to hang around for years and years and years. Some of these cells, again, the ones that are making antibodies, the reason you only have to get your tetanus shot every 7 to 10 years is that those antibodies against tetanus hang around for all of those years, and you get that boosted every once in a while. But other vaccines and other forms of B cells that form antibodies are stable and hang out for most of your life. So again, there is no easy lifespan for these cells from hours to years. If there are too few white blood cells, remember 5 to 10,000 per microliter is normal. If you have too few, you have leukopenia. You know, penia means a deficiency in. If you have more than 10,000, we would say they have leukocytosis. Again, too many, leukocytosis. Leukemia is a term you probably heard. That is a cancer where there is an overabundance of one or more types of these leukocytes. If the overabundance is from the myeloid side, you have a myelocytic leukemia. If it's a lymphocytic leukemia, you have an overabundance of the lymphocytes. Leukemias then come in two different other types. They come in chronic or in acute forms. So again, chronic versus acute. Chronic leukemias, the cells accumulate and fail to die. In acute leukemias, the numbers are usually out of control. And there was an animation for each of them. I'm not going to ask you any specifics about different types of leukemia. Just be aware that in many leukemias, the term myeloid or lymphocytic is in the name, and that gives you a clue as to what sort of cell has gone crazy. Now, lymphomas is a type of cancer where you have these lymphocytes that collect in lymph nodes and also in lymphatic tissue like the spleen, the liver, and other tissues. And so basically, this is a mass of a tumor of these cells that accumulate. So leukemia are blood cancers, and lymphomas are tumors of lymphocytes in lymphatic tissues. Lastly, we'll move to platelets. Platelets are also called thrombocytes. Now, this is not the best name because they are not at all truly cells, but you'll still see them called thrombocytes at times. They are instead a fragment of a cell found in the bone marrow, referred to as megakaryocytes. You can break this term down: mega, large, karyo, nucleus. So these are cells with a very, very large nucleus. This animation will talk to you about platelets, and these in the picture are activated platelets. Now, those megakaryocytes are one of the many types of cells formed from the myeloid stem cells. And here we see a megakaryocyte. That megakaryocyte is going to bleb off these little fragments into the bloodstream, and these little fragments are the platelets themselves. So again, they're quite small, 2 to 4 micrometers in diameter. They are numbering in the low hundreds of thousands. It might be a little bit higher at times, but certainly far fewer than the 5 million red blood cells, but significantly more than the 5 to 10,000 white blood cells per microliter of blood. Again, when they become activated from some sort of damage to the capillary wall, then they will be critically important in the process of hemostasis. We're not going to be studying the steps or the process of blood clotting, hemostasis, but that is a really cool story that you'll learn more about in physiology. And some of you may have heard of PRP. That is when they take your own blood, spin it down, and take out the platelet-rich fraction, including that buffy coat, and they then re-inject that into you. Because these platelets are releasing so many important growth factors, they are able to help with repair of tissues. Likewise, terminology: thrombocytosis would be a condition where there's too many platelets. This could be a problem because your body is now going to be creating unwanted blood clots, right? Thromboses. People who throw blood clots can have significant problems or leading to stroke or heart attack. So too many platelets certainly isn't good. An insufficient number of platelets would be thrombocytopenia, a decrease or a reduction in the number of platelets. This would result in bleeding, which would be a problem. Now, remember that another protein involved in blood clotting is fibrin. Fibrinogen. We talked about fibrinogen as being the third most abundant protein in plasma. So if a person has liver problems, remember that fibrinogen is made in the liver, then you wouldn't have all the necessary components to clot blood, even if there was a need for the platelets to be released. So that brings us to the end of all things related to leukocytes and platelets. Make sure you answer through these questions to assure your understanding of all of the formed elements. Again, we're not going on to 18.5 or 18.6.